Hi everyone. In today's video, we are going to talk about convolutional neural networks, and this is going to be the part one of the series of videos which I will be doing on convolutional neural nets. So, convolutional neural nets or CNNs are used mainly when we talk about images. A particular image will be characterized by three things. First, its width, second, its height, and third, its channel. Just to give a demonstration of how the width, channel and height are captured, I will try to load a sample image in TensorFlow and print the dimensions of the image. As you can see, this is my collab notebook where I try to load an image. First of all, I load the necessary libraries, which are just Matplotlib, TensorFlow and NumPy. I take one small image which is over here, and then if I just run the cell, the first thing I do is to load the image, and then we get few things which looks like this. So this 200 is what we called as a height of the image, and this 200 is the width of the image, and lastly this 3 corresponds to the number of channels in a particular image. This is an RGB image which we are having, so it will have 3 channels. Had it been a black and white image, we would be having just one channel over here. So we will proceed further and we will discuss a very important component in CNN, which is called as a feature map or kernel. So theoretically, a kernel is a small matrix of weights that is convolved with the input image in order to produce a set of feature maps. Now, this entire definition may seem to be a bit difficult to comprehend as of now because it contains terms like, first of all, what is the small matrix, what is this convolved means, and what exactly is the input image. Even though we just discussed input image as something which will be having a height, width and channel, and what are these feature maps exactly doing, we will walk through a very simple numerical example to understand the gist of all these terminologies. And once we are able to do that, then we will be able to scale our understanding up to how a convolution works in TensorFlow, or for that matter any other deep learning framework, and how it helps in the feature extraction steps. Just like when we have a tabular data, we do a lot of feature extraction steps. Just assume that if we are having an image data, we will do all those feature extraction steps with the help of a kernel. Let us consider a very small and a simple example where we consider a 6x6 black and white matrix, or a 6x6 black and white image. It is not having any other channel over here. So this is having just one channel. So this is a 6x6 image. Each and every element over here might represent a pixel. And then we consider a kernel which is of size 3x3. And as of now, just to understand it in layman terms, just consider this term kernel as to be a feature extractor. So it is just a feature extractor. So now the thing is, how are we exactly going to use a given kernel K on an input image A to obtain an output image which is supposedly the feature map of the input image? So ideally we will have an input image of a certain dimension which is 6x6 over here. We will have a kernel of another dimension 3x3. Since we are not dealing with 1D arrays, we are actually dealing with 2D arrays, or in many cases like 2D arrays with a channel added as well. So we need to extract the feature in a particular way. So in order to do that, we use the kernel. Now the issue is, how are we exactly using these kernels to extract the details from the images? So we consider the convolution operation where the kernel is slid across the input image, and the dot product between the kernel and the small local region of input image is computed for each position. The extent to which a kernel is slid is called as a slide. So this is how it works. Now, just to give an example, I will just perform one small calculation of the dot product for extracting the feature. So now just let me consider that the output matrix is going to be H, which will be some Hij. I, as of now, don't want to comment about the dimension of the matrix H, but it definitely will have the first element, which is going to be H11. So now just to throw a light on how the calculation will be working in the case of H11, we will consider the first 3 cross 3 matrix or the submatrix of the given matrix A, which is this. This is the 3 cross 3 submatrix of A, and K is the feature map or the feature extractor which we are having. Now we calculate the dot product between the elements of the first 3 cross 3 submatrix and K. This is exactly what the definition meant, that the kernel is laid across the input image and the dot product between the kernel and the small local region of input image is computed. Now the small local region of input image is what exactly I am highlighting over here, and the kernel which we have is shown over here. This is the kernel. Now in order to calculate the dot product, it's pretty simple. We just have to multiply this term 3 with 1. We will be multiplying this 2 with this 2. We will be multiplying this 7 with this 2. We will be then multiplying 4 with 2 and 1 with again 1 over here. We multiply 1 with 2 over here. We multiply 8 with 2 and we multiply 2 with 2 and eventually 0 with 1. After performing all the multiplications, we add them up so as to get the dot product, which somehow looks like this. So this is exactly the how the first element is supposed to look like when we have 3 cross 3 convolution running or 3 cross 3 kernel running on a 6 cross 6 matrix. So at least we are able to get the first element. We don't know what is the extent till which we will be getting it. Now what we do, we take the same image and we take the next subset of three elements from the matrix, which looks like this. So this is the next subset of three elements, the one which I have highlighted. I consider that and try to find the next term h12, and once I am able to calculate h12, I can calculate h13. If I consider this part, I will be able to calculate h13, and eventually the three of the elements which will be left, we will be able to calculate h14. At least over here we are able to see that the each row will be having 4 columns, but we don't really know how many rows are going to be in the first place. To do that, we perform the same operation now row wise. So I will move to it, but as of now, for the sake of simplicity and to make everyone accustomed to how a kernel works, we will calculate 2 or 3 more values before we jump into finding out how many rows actually are there and generalizing the result. So I proceed a step further and I look into the matrix which I have. We can see that we are considering this matrix, the one which I am highlighting over here, and simultaneously we have this kernel over here as well. So on performing the multiplication of the dot product as per the definition, we multiply 2 with 1 over here, 7 with 2, and eventually 1 with 2, and 1 with 2 again, 1 with 2, 1 with 1 again, 0 with 2, 2 with 2, 0 with this 2, and 1 with 1. So eventually we get the value as 26. So now we add one more observation to the two operations we have performed till now. So what we observe is the fact that there are 9 multiplications needed, which is equivalent to the size of the kernel or the feature extractor. So the size of the kernel was 3 cross 3. So that comes out to be 9. So there are 9 multiplications which happen, and corresponding to the 9 multiplication, in order to calculate the dot product, we perform 8 additions to it. So this is a very small value when we consider the size of the image to be 6 cross 6 and the size of the kernel to be like 3 cross 3. Even with that, it's a very small value which we are getting, but usually we won't be having just one kernel at place. We are going to have like tens or 15s, like 10, 20, 30, 40 kernels over there. And if we are talking about realistic images are actually going to be at least of 256 cross 256 size or even more than that. So the number of operations when we perform one convolution is increased exponentially when we increase the size of the image, and likewise when we increase the number of kernels which are going to be applied on that image. Now we proceed further for the calculation of H13, and like we saw in this example, I will be using the same image and do the calculation for H13 as well. For the calculation of H13, we consider this submatrix, and consequently we have the kernel as usual, and just we follow the same terminology for calculating the dot product. We consider the first row and we multiply with the first row of the kernel and add it. Likewise we consider the second row 1 0 and 9 and multiply it with the kernel 2 1 2, and the third row eventually becomes 0 1 2 and multiplied by 2 2 1, which comes out to be 45. We do the same calculation for H14 as well. Like as of now, this is what we have covered. If H is a matrix, we were able to capture H11. We know what H12 is. We know what H13 is. We know what H14 is. At least we are able to capture the first row completely. Now we are in a position to generalize things in a bit. Like if we have the H14 and if we write it in the abstract way as to how it is going to look like. So if you see the H14 calculations over here, yeah. So if you see the H14 calculations over here, it took into account this term, and this term. All the three terms are A14, A15, and A16. Likewise, we have A24, A25, and A26, A34, A35, and A36. So all these six terms are written along with the fact that we write the kernel terms as well, K11, K12, and so on. So we kind of get a relationship which looks like this. Now it can be generalized in a better way. We are assuming that the indices are starting from 1, like this is how it is supposed to increase. It starts from 1 and it increases. Likewise, for the column, it starts from 1 and it increases as we go down the lane. Now we can write it in a generic way, like if I have to write H1 for the entire operation over here. So we know that Kij is a constant. What we can do in this scenario is change the value of I and j over a loop. We can say that if j is equal to 1, sorry, if I is equal to 1, then j can have different values like k11, k12, k13. Likewise, we can proceed further with the second row and third row, and this will all continue till f. F is ideally the size of the kernel, right? Size of kernel. So f in our case is going to be 3. So we proceed further, use the same formula we did previously to calculate R21, just the abstract formula which we have used till now, and on solving we get this. Now, just to highlight, there is a small typo over here. So this is ideally something which is like A. It is not H. H we are actually finding out. Yeah. So let me rectify it. Yeah. So we proceed further and we calculate the value of H22, H23, H24 in the same way. And likewise, we now know that the second row is having 4 elements as well. Now, how exactly I am calculating the value of these elements? And just to throw a context, how am I calculating exactly to how to this H21 value? It's calculated like this. Since we have to calculate the H21, we consider this submatrix completely, like 411, 820, 560, and then we have the kernel matrix over here. And then we use the same formula for HMK as we have defined a bit before. The only thing is here M becomes equivalent to 2 and K becomes equal to 1, and the value of I and J is anything between 3 and 1. So that's what it is shown. So the first thing is a m plus I minus 1. It's like m is 2 and I put I as 1 over here, and it comes out to be 2 only. And likewise second index k plus j minus 1, it's coming out to be 1 over here, and then we proceed like we are just putting the values of means I and j with suitable m and k, and then we are able to get the complete convolution done over here. So the answer to that H21 was 48. We do the same for H22. We proceed in the same way. H23 and H24 follow the same route, and then we proceed to the third last column, which is H3. The values corresponding to H3 are exactly calculated in the same way. The image is a bit blurred, but just bear with me. So we get H3 and H4 calculated, and eventually we are almost in the last leg of the derivation, and we get something which looks like this. So we do all the operations over here, and eventually when all the operations are done, this is the output matrix we are getting. So we were given an input matrix of order 6 cross 6. We did apply a convolution using a kernel of order 3 cross 3, and eventually we get the feature extracted in the form of an output matrix H of order 4 cross 4. So for one value of H, we do around 9 multiplication and 8 additions. Now if I have 16, like 4 cross 4, 16 values of H, we are straight away doing around 144 additions and roughly about 144 multiplications and 128 additions as of now. And this is a very small image, 4 cross 4, which is practically nothing. Each of these kernel perform a specific task. Like some of the kernels will try to blur the image, some of the kernels are meant to identify the edges, some of the kernels are meant to identify the horizontal and vertical edges, and all these kernels do their task respectively. Now if we have to consider the amount of operations a particular kernel has to perform, it increases exponentially whenever the size of the image increases. So having said that, we were able to get a 4 cross 4 output image from a 6 cross 6 input image using a convolution kernel of order 3 cross 3. Now we didn't knew that the output image is going to be 4 cross 4 in the first place. So on careful observation, it was seen that there is a formula which is used to find the size of the output image, provided that we know the size of the input image and the size of the kernel. And the formula kind of looks like this. So we consider an n cross n input image. In our example, n was equal to 6, and we had a 6 cross 6 image, and f cross f is the kernel size, and by that we mean that the size of the kernel in our example was 3 cross 3. And just take this thing for granted, as of now the stride is s. In our example, s was equal to 1. So I'm not writing it explicitly because it is a standard notation. And now if we consider these constraints, then we can see that the output matrix after the application of convolution or after applying the feature map is going to be of this size. This is a floor function which I am using. I am considering the input image size, and this is the kernel size, this is the stride, which we assume to be 1 plus 1. So in our case, n was equal to 6, f was equal to 3, then the size is supposed to be 6 minus 3, and the stride was 1 of course, plus 1. And if I lower limit or I apply a floor on it, it comes out to be 4. This is exactly how the size of the input image was determined previously when we were solving it. Even though if you start solving it, you try to perform one calculation after the other, the moment you hit a dead end, you don't go further. So if you proceed with that, you will definitely be getting a 4 cross 4 matrix without even knowing that you are getting a 4 cross 4 matrix. The only advantage of the formula is, which I'm writing over here, is the fact that if you know the input matrix size, and if you know the kernel size, then definitely you will be able to understand how the output size is going to look like. And it plays a very important role, specifically when we are using some TensorFlow or some framework like TensorFlow for performing such convolutions, because it's very strict on understanding how the internal structure of the images and how the images are being reshaped before passing to a particular function. We will look into that in detail as well, but as of now, the important formula which we were able to derive is the size of the output matrix. After performing the convolution, it is going to look like this. And now if I consider the number of multiplication which is supposed to happen in the previous example, or the example which we were discussing, the number of multiplications were considered to be 4 cross 4 into 9, right? Because 4 cross 4, why it's coming over here? Because that's the size of the output image. Now the size of the output image in our case is going to be this. So the number of multiplications are definitely not going to reduce below this. It's going to be the multiplication of both. And then in our example, we used to multiply it with 9. And 9 represents 3 cross 3, which is exactly the size of the kernel. So to make more generic, we multiply it with the size of the kernel. That's it. The only difference between multiplication and addition is, if I am adding 9 quantities which are being individually multiplied, then multiplications will be 9, but to add those 9 quantities, only 8 additions are needed. That's accomplished over here, and then we are able to find the number of additions as well. So this is what is exactly demonstrated in the formula for convolution. So now we are going to bring our discussion to a TensorFlow framework, and we'll try to see how the filters or the kernels are incorporated over there. So I come back to the usual image for which I showed the demo previously. Like, I consider the image of Spider-Man over here. Like, it's a 200 cross 200 cross 3 image, RGB image is there. Now we need to apply a kernel. So what I did, I said that I need a kernel of size 3, like it's a 3 cross 3 kernel, and I need 3 such kernels because the input image is going to be of size 3. Or the number of channels in the input image is going to be 3. So only one kernel will not be sufficient. Definitely we will be needing more kernels. At least 3 is definitely needed. And then we proceed further to get a parameter like this, like what is the input shape of the image. Over here we start from here, like from 200 height, width and channel. This first parameter is ideally what is called as a batch size. Unless we are doing a batch processing, we can keep it as 1 only, and since it is just an example, we just keep it as 1 and see exactly what we are getting. So I considered a sigmoid activation function, and on running, so this is what I am getting over here. You can clearly see something is being extracted from the kernel matrix, which is randomly generated internally behind these codes. Like, it's completely happening in the backend. So based on that kernel, this is how the image is going to look like. So let's not restrict ourselves to just 5 cross 3 cross 3 kernel. I just do a little bit more experiment. I use a 5 cross 5 kernel, and then I see the size of the image and the resultant output, which looks like this. Now there are a few things which are very important and can be captured over here. Like, if I see this image properly, this is ideally a 200 cross 200 cross 3 image. Now let's use the formula which we had in the notebook. So this is exactly what is happening. So the size of the input image is 200 cross 200 cross 3. Here n is equal to 200. Here the number of, so the kernel is of size 3 cross 3. Here f is going to be 3. Now I apply the formula for the output size, which is equal to n minus f divided by s plus 1, and we take the floor of this function. Here n minus f is 200 minus 3, and the stride as of now is 1. We add 1 to it and take the floor of it, it comes out to be 198. So we know that the output image which we are going to get is somewhat like this: 198 cross 198 cross 3. That's it. Now we go to the code, and this is exactly what we got over here after the first convolution of order 3 cross 3. This is the shape which we got after inputting a matrix of order 200 cross 200. Now let's try to experiment like I experimented over here with 5 cross 5 kernels. Now it showed the value as 196. Let's go back and check if it is the value which we are supposed to get or not. So I come over here and I write the value of n as 200, value of f is equivalent to 5, and stride is definitely 1. The size of the output image is going to be like this. So n minus 5 is 195 divided by 1 plus 1 is 196. So the output image is going to be 196 cross 196 cross 3, because we have 3 kernels. So I go over here, we see exactly the same thing which we expected, like 196, 196 and 3 is exactly what we need right now. And the image kind of looks somewhat like this. Now if I run this code again, this is how this is what I'm trying to show. I'm getting a completely different image altogether. This is happening because the kernels are actually learned while the neural network training is going on. If you are fetching any layer and trying to find out the edges out of it, it will definitely detect it, but the image resolution will be quite poor as it is shown. The weights in all the kernels are learned during the training process, and they determine the specific feature that the kernel is designed to detect. So not all the kernels are going to do the same operation over and over again. It might be possible that there are some operations like edge detection or finding out the blur of the image which can be done with some set of kernels, as they determine the feature extraction steps, and the corresponding weights are learned during the training process. And when we talk about the training process, it's one forward and backward pass of the entire network. So we just saw an example where we had a 6 cross 6 matrix, and for a kernel of size 3 cross 3 we were able to perform the convolution and get the result in the form of 4 cross 4 matrix. Now the thing, we also demonstrated the same using TensorFlow Keras, and we were able to find out the reasonable weights for the same. In real sense, the data is not going to be too small. This is just for demonstration purpose I picked up. So that concludes this video over here. Uh, do prepare the notes while working on this topic, because a lot of things might be skipped because the entire convolution process is a bit tough, or I should say tougher than how a perceptron is calculated. And once done, you can do a check on the size of the output image attained using this formula. So I think that's it for this class. In the next class, we will be discussing few more convolution techniques like dilated convolution or transpose convolution, and also give a brief intro about how a convolutional 1D looks like. Thanks for your time.